Hello everyone, this is Puya. This video is about combinatorics. It's a mixed lecture about permutation, combination, and a little bit about probability. Let's start with a little bit of basics about set theory. So if you have two sets of A and B, the union of two sets is the set of all elements found in either A or B. So A union B is comprised of all the elements in A or B. And the word or here is used here to mean the union of set A and B is the set of all x such that x belongs to A or B or to B or to both. Okay, it's not like it's basically similar to logical OR that we have. It's not an XOR, it's an inclusive OR. For example, if A has elements including 4, 5, 6, and B has 6, 7, 8, then A union B would have 4, 5, 6, 7, 8. We call a set an empty set, and we use it using the symbol, using this symbol, like the Greek letter phi. It's the set that has no elements. So A union with an empty set, it's going to give us the same original set A. Also, the intersection of two sets A and B is the set of all elements in A that are also found in B. So it's basically the common elements between A and B. For example, if A is, again, 4, 5, 6, and B is 6, 7, 8, then A intersection B is only 6, because 6 is the only element that's found in both sets. If two sets A and B have no elements in common, they're called disjoint. So A intersection with B is an empty set for two disjoint elements. It means disjoint sets means that these two sets have no common element. And A intersection with an empty set, it's going to be an empty set. So if we consider all college students, then set A, let's define it as students who are born in 1980s, and set B, students who are not born in 1980s. These two sets are disjoint. Their intersection is an empty set, and their union is going to give us the whole students at the college. Another concept is Cartesian product. So if we have two sets A and B, we define their Cartesian product A cross B to be the set of all ordered pairs A and B, so that A, this lowercase a, belongs to the first set, in this case capital A, and lowercase b is an element from the second set, in this case capital B. So A cross B is the set of all ordered pairs A comma B, for which A is an element of A and B is an element of B. So it's basically paired elements. For example, the xy plane that we are all familiar with can be defined as the Cartesian product of the set of all real numbers. So it can be defined as the Cartesian product of the set of all real numbers producted with itself. Then the plane is defined as the set of all ordered pairs x and y of real numbers. Another example is given here. So let's say that we have three sets, x, y, and z. X has only elements 2, 4, 6, 8, 10. Y has elements 0, 5, and 10. So they're discrete sets. And z has all the elements with real numbers between 2 to 5. This is a continuous set, right? It has like infinite number of elements. Then the set x cross y cross z can be visualized as shown here. So you see that x only takes values 2, 4, 6, 8, 10. Y takes 0, 5, and 10. And z takes all the values between 2 to 5. Okay? So this is the Cartesian product or the cross product of x, y, and z. Suppose now we are organizing a VCC project expo. You're going to have the groups of two. You're going to have to organize groups of two. One engineering student and one science student. So we want to have each group to have one engineering student and one science student. The set of all possible combinations are can be found by the cross product between these two sets, set A and B, where set A is the set of all engineering students and set B is the set of all science students. The addition principle. The addition principle is a fundamental counting principle which states that we may add mutually exclusive options. It means options that cannot happen at the same time. That's what mutually exclusive means. Stated simply, if we have m ways of doing something and n ways of doing something else without being able to do both, then either of these tasks can be done in m plus n ways. I'll give you an example. Let's say that we are gonna go to a restaurant to have dinner. We have two options, restaurant A or restaurant B. In restaurant A, we have 3 options for food. In restaurant B, we have 5 options for food. How many total options do we have for dinner? We have 8 different options. If we go to restaurant A, we have 3 options. If we go to restaurant B, we have 5 options, right? And we assume that we can only go to one restaurant. So these are mutually exclusive options. And like we assume that we only have one main dish, right? So that's why they're mutually exclusive. And so if we have n ways of doing something and n ways of doing something else without being able to do both, like without these tasks happening at the same time, then either task can be done in m plus n ways. And this can be expanded. In general, if there are k events that cannot occur at the same time, let's call them E sub 1, E sub 2, all the way to E sub k, such that E1 can occur in N1 different ways, and E2 can occur in N2 ways, and so on, then the total number of ways for at least one of these events to happen, it's going to be the summation of N1, N2, all the way to Nk. So it's the summation of Ni's. So this is like the example I just gave you. So let's see this again. Let's say like you have the option of either going for dinner or seeing a movie, but not both. There are 3 restaurants to pick from and 5 different movies currently playing. Then by addition principle, you have 8 different ways of spending your evening. More formally, according to set theory, addition principle can also be described using set theory. So let a sub 1, a sub 2, all the way to a sub k be any k finite sets where k is bigger than or equal 1. If the given sets are pairwise disjoint, it means like their intersection is empty. Also like means they cannot happen at the same time. So if for any pair they're disjoint, the sets are disjoint, then the number of elements in the union of all these sets, right? So like the number of elements in the union of A1, A2, A all the way to AK, it's gonna be the summation of the number of elements in A1 plus A2 plus AIs all the way to AK. Okay. So this basically, according to set theory, this is like what addition principle means. This is a very special case of a bigger theorem, right? So like there is a more general format of this theorem, like for the case that the sets are not disjoint and like you would have multiple terms. But for the case that all the sets are pairwise disjoint, this is what the addition principle is reduced to. In our previous example, we can denote the set of all possible places to eat, all these different restaurants that we have as set A. So we have 3 different restaurants in set A, and set of all possible movies to see as set B. We had 5 different movies in set B. And since A and B are disjoint by addition principle, we have 8 different things to choose from for the night. So let us consider all students in VCC. Let's define set A as all minor students and set B as students who are not minor. A intersection B is an empty set. A union B is all the students at VCC at any college. So this should be the union. So the number of elements in the union of A and B is the addition of number of elements in A plus number of elements in B. This is an example shown here. Find the number of ordered pairs A, comma B, where A and B are elements of the set X, such that A minus B, absolute value of A minus B is equal to 5. Okay, so we want to find like how many different pairs of A and B we can find so that they have this property where A and B are chosen from set X. Okay, so first of all, we can simplify this condition. We can basically make it like 2 different conditions. So either A minus B is equal to positive 5 or A minus B is equal to negative 5. Right, so these 2 conditions are disjoint, right, because they cannot happen. Either A minus B is equal to 5 or is it equal to minus 5. It is, if it is equal to 5, then we have this relationship between B and A. If it's equal to negative 5, then we have this relationship between A and B, or the other way around. Okay, I might have made a mistake. If A minus B is equal to positive 5, this is the relationship we have between A and B. If it's equal to negative 5, this is the one that we have, the relationship between A and B. So for set 1, A can be any number between 1, any integer number between 1 all the way to 45. It cannot be bigger than 45, because if A becomes bigger than 45, then B cannot be in the set X. So A can be any number from 1 to 45, and for any A, you can find B by adding A with number 5, positive 5. Right, so these are all the pairs in the set S1 where B is equal to A plus 5. Set 2 are the pairs that satisfy the second condition. Okay, in this case, A can be any number from positive 6 all the way to 50, positive 50, or any integer number between positive 6 all the way to positive 50. It cannot be anything smaller than 6, because if A is less than 6, then B cannot be in the set X, and of course it cannot be bigger than 50 because A should be chosen from set X. So again, for any value of A, you can find B, which is also going to be in set X. Okay, so the number of elements in set 1, S1, it's going to be 45 pairs. For set 2 is also 45 pairs. So the number of pairs of A and B that satisfy this condition, it's going to be 45 plus 45. Right? S1, the number of elements in S1 is 45. The number of elements of S2 is 45. These two are disjoint, means S1 intersection S2 is an empty set, as they do not share any element. So therefore, by addition principle, the number of possible pairs of A and B are 45 plus 45 is equal to 90. In more general term, if we have two sets, the number of elements in A union B is going to be the number of elements in A plus the number of elements in B minus the number of elements in A intersection with B, right? So in this case, this is a special case where like the two sets are disjoint. So it means like A or S1 union S2 is going to be number of elements in S1 plus number of elements in S2. The multiplication principle. So the multiplication principle is the second fundamental counting principle. Stated simply, if we have m ways of doing something and n ways of doing something else, we can do both things in m multiply n different ways, provided that they are independent of each other, right? So the choice of like these n tasks and these m tasks are not going to affect the other one. Okay, as an example, so let's assume that this evening you are planning to go for dinner followed by a movie. So you're going to do both tasks, and the choice of your dinner is not going to affect what movie you want to watch, or the other way around. The choice of your movie is not going to affect what you're going to eat. If you have 3 different restaurants to pick from and 5 different movies to choose from, then you would have 15 different ways of spending your night, right? So like depending on so you have 3 options for the dinner, and for each option you have 5 options for movie, right? So you would have total of 3 times 5, 15 different ways to spend your night. And this can be expanded for like our different tasks, or different or our different events. If an event E is composed of R independent events, this term independent is critical here. E sub 1, E sub 2, all the way to E sub R, such that E1 can occur in N sub 1 ways, E2 can occur in N sub 2 ways, and etc. Then the total number of ways for the event E to happen is given by the multiplication of all n i's, where I goes from 1 to R. And again, more formally, multiplication principle can also be described using set theory. So we can just consider the Cartesian product of R different sets, A1, A2, all the way to AR. So basically we have some sort of tuple like of different events, A1 all the way to AR. So we want to figure out like what is the number of elements in this Cartesian product set, right? So like in this Cartesian product set, the number of elements, it's going to be the number of elements in A1 multiplied by the number of elements in A2 all the way to number of elements in AR, and you can denote that using the expression given here. To help visualize the previous definition, consider the following two dice D1 and D2. Like we roll them. How many different rolls can we obtain? Right. So these two die are independent, right? So each of them can have 6 different outcome, right? So there are 6 elements in D1, 6 elements in D2, right? If we roll them together, right, the pairs that we can get, it's going to be 36 different pairs, right? So and these like shows all the pairs, like 1 and 1, 1 and 2, 1 and 3, 1 and 4, 1 and 5, 1 and 6, and so on. And this can be visualized here, right? So the number of elements in this Cartesian product set, it's going to be 36. Since it would be inefficient to list and count all ordered pairs that result from the Cartesian product, as shown on the right, we can apply the multiplication principle. So instead of just counting, like we can just like answer this by the multiplication principle. Okay, so what if we're gonna roll it 3 times, right? What if you have 3 dice? If that's the case, right, if you have 3 dice, then the problem again can be solved using multiplication principle, and then we would have 6 raised to power 3 different outcomes, or like 216 different elements in this set. Let us consider all students in VCC again. So students wearing green would be set A, students wearing blue is set B. There's no common element in these two sets, and A cross B would be, or A Cartesian product would be, it's going to be all the possible couples that we're going to make out of these two sets. So the number of couples that we can have is going to be the multiplication of number of elements in A by number of elements in B.